Hi, my name is Matt Broker, and I'm from Johns Hopkins University. I'm presenting on some joint research that was done between myself and Stephen Checkoway, who just presented. And we're talking about the MacBook iSeeYou proof of concept application that we created, and it shows how we can disable the webcam indicator in the MacBook LED. So I want to start off focusing on embedded systems. On the right, we have actually a toaster. We don't normally think of this as an embedded system, but this is a very special kind of toaster. You see, this toaster is connected to Wi-Fi, and it can actually create toast that prints out the weather report for the day. And so what we've done here is we've added an external connection to this toaster, and we've added an embedded system within it that connects out to the internet and pulls down a weather report. And then on the left, we have a vehicle, and what's interesting about this is we can look at it from face value and just see a car, but once we dig in deeper, we can see a bunch of different systems within it, interconnected, and each of these as well connect to one another and have external connections. And when we do this, what happens is when we create communication for one another and external communication, we leave the possibility up for vulnerability to arise and for malware to run on these systems. So now let's look at the computer. And we can look at it as a computer, but then we can start to look down at some of the different components, these embedded systems within the computer. And what's interesting is each of these have processors. So really, what I came here to tell you is that your computer is full of a bunch of different toasters. And so these are systems that have processors, and they're running embedded code on them. And then that means they each have varying different levels of access to the system, which means that they could potentially be vulnerable. So the toaster we're going to talk about today is the MacBook iSight. And this has a Cypress Easy USB microcontroller on it. It's an 8051 architecture, and it's called an Easy USB because the vendor created it so they would be easy to use USB. And it's got some extra libraries in it so that it could easily packetize the data and send it to and from the host system using the USB. We're most interested in the LED in this case, and this is a privacy-enhancing feature. And the idea is that when the camera's on, the LED will be on, and it will let the user know whether the camera's in use or not. If the LED shows up and the user isn't using their camera, then they know something is wrong with the system. So at this point, you might be wondering, why do we care about this LED? Well, there's actually, this has some real-world ramifications. There's a number of different groups that would potentially be interested in surveilling people on their computers and using their cameras. One of them would be nation-state actors. And the FBI has actually made the statement that they've had the capability to use this LED and actually disable it when using a camera. And others are stalkers on the internet. There's this group that's referred to as ratters. They use remote access toolkits. They install them on people's computers and surveil them that way. They don't have a capability to disable the LED that we know of. And then finally, anyone who gives you a computer. So there was a school district, Lower Merion School District, who gave students computers, and they took them home for home use. And later, actually, the school district was accusing one of the students of doing drugs. And the reason why, they provided some evidence of some pictures of the student, and it turns out the student was just eating candy. It wasn't drugs. But they had this software installed on the student's computer that would take pictures, and the LED would briefly flash. And then finally, in the future, we care because biometric authentication would be using our webcams, and if someone's using our webcams, taking pictures of us without us knowing, then they could potentially use those pictures to authenticate to our services. So we sought to answer this high-level question, can we turn the LED off while the video is recording? And Apple makes the claim that this is not possible. They've designed this through a hardware solution. We wanted to find out, though, if malicious firmware were able to get on the iSight camera, would it be able to disable the LED? And then finally, if that's possible, then could malicious software on the host computer upload firmware onto the iSight and then have control of that LED? So we answered this through a combination of hardware and software reverse engineering as well as experimentation. And right now I'm going to show you some of the hardware. So this is the camera from an iMac G5, and we purchased this off of eBay. We also purchased a few different cameras. They were all from 2005 to 2008 Apple products. We got the MacBook Pro, and then the iMac G5. And here we can see some of the different components within this embedded system. On the upper right, you can see the LED, and that's that privacy-enhancing feature that we're interested in. We want to know what controls it. On the left, we can see the USB, and that's actually how the camera communicates with the host device. So software programs will communicate over USB to say, hey, I want to use the camera, and then it'll receive the video that way. And then next, we have the microcontroller in orange. And this is that easy USB processor, the 8051 architecture that I mentioned. And when you look at this, you notice some interesting connections. There's an I2C communications bus, and the microcontroller will communicate with the other devices using that messaging bus. And then we also find a connection over to the LED from the microcontroller. So at this point, we wonder, is the microcontroller the one controlling this LED? Next to the microcontroller, we see an EEPROM. And this is the only non-volatile storage on the camera. At first, we thought maybe this is storing the firmware for the iSight camera. It turns out this is only 16 bytes of storage, and it's just some configuration registers. It's the VID and the PID. When the USB device enumerates itself, it identifies itself as the Apple iSight, and so that's just storing a few 16 bytes of values there. That's connected to the I2C, and so the microcontroller will read those values at the start when the camera's plugged in. And then we also have the image sensor. And the image sensor, we notice a connection as well to the LED. And so the image sensor is actually the device that captures the video, and then it's sent over a data bus from the image sensor, 8 bits, over to the microcontroller. The microcontroller will packetize that data and then send it to the host computer. The image sensor, just from looking at it, we weren't able to tell the exact model number of it. And we were interested in figuring that out so then we can figure out what are those connections on the image sensor to the rest of the system, and then specifically which is the connection that's connected over to the LED. So in order to find out more about this image sensor, we found out that when the device enumerates itself, it identifies itself as a Micron device. So that's our vendor, and we went to their website to try to see, can we find different image sensors that match the specifications of what we know the Apple iSight camera has. And we were able to narrow it down to 5 different choices here, but we weren't able to narrow it down further because they all seemed to match the specifications. So we needed to, at this point, narrow it down even further. And what we did is we downloaded the data sheets off of all 5 of these, and we tried to take a look a little bit more at them. And so one thing we noticed in the data sheets is, so these image sensors contain registers. And actually the microcontroller, the 8051 Easy USB, will, once the device is plugged in, it starts to configure these registers. And so it'll change things such as the amount of red, green, blue that's on the camera. But then another thing that we noticed was that one of the registers the microcontroller can query is the chip version. And so that would give us the exact model number of this image sensor, so we know what we're dealing with. And so we ran a quick test where we had the microcontroller query the image sensor, and it gave us back the register value for the chip version, which is 1229 in hex. And then that told us that this was the MT9V112 image sensor. So with that out of the way, we poured through the data sheet to see what else we can learn about this device. We wanted to start to determine which is the connection connected to the LED from that image sensor. And so reading through this, we looked, this is actually the typical configuration on the data sheet for how you would connect this image sensor to a system. And we were able to narrow down the connections down to a standby connection. And that seemed to be the input into the image sensor that was connected to the LED. And so reading more about the standby, we were able to determine that the purpose of standby is the microcontroller, the 8051, can tell the image sensor to go into a low power state. And if it goes into a low power state, the video feed will no longer flow from the image sensor back to the microcontroller to be packetized and then sent to the host application. And so this is a useful feature because it will allow the microcontroller to configure all the registers it needs on the image sensor, and then after that it doesn't have to configure them anymore. It can just put it into standby when it's not using it. It's in a low power state, but then when it needs to use it, it'll take it out of standby, and then video can flow again. So now we've seen different aspects of the hardware here. Let's take a step back and look at what we have here in this iSight architecture. We saw that there's a USB connection to the host. We've seen that the easyUSB processor, the 8051, can configure the image sensor via I2C. We've seen that there's 16 bytes of an EEPROM, which doesn't really matter to us as much because that's not storing the firmware that we're concerned of. And then we see the standby connection, and that's used from so that the easyUSB can put the image sensor into low power state when it doesn't need to see its video. So looking a little bit more through the data sheet, we are able to find this reset register. And you'll notice there's 2 bits here. And it's interesting because this basically allows you to inhibit the standby signal on the image sensor. And so the image sensor might normally be receiving in hardware a signal that says, hey, go to sleep, I don't need video from you anymore. And this would allow the microcontroller to configure it so that it would ignore that hardware state. And let's remember, too, that the LED is connected between the microcontroller and the image sensor. And so basically, that's the hardware line that provides the security. So considering for a moment, if malicious firmware could somehow get itself on this processor, well, what could it do with this standby? So basically what malicious firmware could do is it could set that reset register via I2C, and then that would tell the image sensor to ignore standby state. No matter what I'm sending to you over this connection, this hardware connection, I want you to always be sending me video. And what that does is it gives the microcontroller independent control of the LED regardless of video. So it can always be receiving video, but it can decide whether or not it wants to display that LED light or not. So in order to make this a remote attack, we need to understand a little bit more of how does firmware normally get loaded up onto this iSight camera. And what we see is the iSight is connected to the internal high-speed USB bus. And there's an Apple USB video support kernel extension. This is an IOKit driver. And that driver is sitting waiting. And if there's a USB device connected with the vendor ID and the product ID matching the iSight, then it's going to upload onto that device the firmware. And so once this firmware is uploaded, it can configure the different registers on the image sensor, and everything's up and ready and going. And then any host application on your computer can then use this as a camera. So one thing we noticed that was interesting is that that firmware load process actually doesn't need to be done by a root process. A non-root process could upload firmware onto the iSight image sensor. And also, at any point in time, the firmware can be re-uploaded onto the image sensor. And that leaves this wide open for an attack from the host computer. So what we have in this scenario is we have malware running on the host system, and it's going to choose to upload some malicious firmware onto that easyUSB processor. From there, the malicious firmware will issue a command over to the image sensor to disable standby, which gives it that independent control of the LED, regardless of, even though video is always being sent out. And then at that point, our host computer has control of that LED and can always be seeing video. So now I'm going to show you a demo of just that. So here, up on the screen, we have this is our proof of concept application, the iSeeYou. And I'm holding in my hand, this is an iMac G5 image sensor camera board, and this is an iSight camera. It's from 2008, and as I mentioned, all the cameras we got were from 2005 to 2008. And so right now I'm going to start using this camera. And people in the front can tell that the LED is on. And we can see the crowd here. And so now what I'm going to do is I'm going to disable the LED. And you notice the video is continuing throughout this whole time. So I can independently enable and disable the LED regardless of, in the whole entire time the camera stays on. So at this point, we have an attack vector where malicious software on the host computer can, as a non-root process, upload arbitrary code onto the image sensor and do what it wants with that and disable LED. And that's our main finding. But we wanted to say, what else can we do with this? And so if you read the paper, you'll see that we have an attack here showing how you could potentially break out of a virtual machine. And this is using basically we configure the camera to re-enumerate itself over USB as a keyboard. And so if a virtual machine were using the camera, then it could be re-enumerated, and then at that point, it could start executing code as a keyboard onto the host system, and you can read more about that in the paper. So what are some of the conclusions from this finding? This is a 2005 to 2008 camera. It's not necessarily up to date. And well, one of the conclusions we find is that we find the LED actually does have privacy and security implications. And in this case, we see that the feature of the LED is important to the user because for a normal user, that's the only way they can tell if their camera is in use. And in this case, we see that it doesn't even do that, its sole job. And so in some cases, this is an example of a software circumventable defense. So Apple designed in hardware a connection to couple the LED so that when the camera's on, only the LED would always be on. But here we see that you can disable it in software. And in some cases, we really do want the hardware to have the final say. Also, we see processors and computers are vulnerable. There's a bunch of different processors, those toasters that I mentioned at the beginning. And each of these has varying levels of access to the system. And they weren't always designed with security in mind. And so as security researchers, we need to take a look at these devices and bring them up to speed with the rest of the computer. And then finally, we see that security is a systems problem. So we saw the system fail at varying levels. As users, we trust our cameras and our computers. We trust them to do what they say. We saw that the host operating system allows any user process non-root to upload. And then we also found that there's a software override to the hardware mechanism. And so even though the hardware team thought they maybe designed this to be coupled, the LED to be coupled in hardware, the image sensor team who chose this particular image sensor didn't realize maybe the ramifications that there's the software override here. Thanks, everyone, for listening. And at this point, I'm happy to answer questions.
All right. So we have a microphone over there, or walk up to me and I'll hand you this. Go ahead.
Hello, my name is Andrei Kostin from Eurocom. Thanks for the nice talk, awesome work. My question is coming from also CCTV research area, and this problem is also not only to webcams, but in general all video imaging devices which are hackable. So could you give some vision on how to actually fix without mechanical fixes, like putting something in the front? Because in CCTV we can see the same problems. And do you think that a hybrid software-hardware solution would be a good one, or tainting the video feed so it can be captured at low kernel levels? Like, could you?
Right.
Thanks.
Sure. Yeah. So in our paper, you'll read a number of different defenses that we proposed here. The problem, yes, as mentioned, is that we have a hardware device that's already deployed, and we find a flaw in it, and we can't exactly remanufacture these devices for computers that are already out there. And so we had a few different software defenses. We can make it so that a root process would only upload new firmware onto this image sensor. But really, I think the final solution is for future versions of these cameras. We want to design them with hardware only with the LED, and there's no software override at all of the. So we need to, as a systems problem, we need to choose an image sensor that doesn't contain a software override to the hardware line.
Yeah, I guess you sort of answered my question, Rachel Greenstadt from Drexel University. But I was wondering that, like, how specific is this to this problem? Do you think it's possible to do like an LED indicator defense and find it trustworthy, or do you think it's in all cases you should just put a sticker over your camera and assume that it's broken?
I mean, obviously the surefire way would be to put the sticker over a little slider over your camera. But I think that, you can do a secure design with the LED here so that in hardware someone would have to deface the device to actually affect the LED. And I think that is probably an amount of security that most people are comfortable with. Someone would have to have physical access to my device and actually mess with my camera in order to change the LED state. And so basically, what we found is the image sensor that they happen to choose contain that software override, but if you swap out image sensors for one that didn't have that standby, inhibit standby function, then we would have a hardware connection as Apple intended.
Did you talk to Apple about what you found, and what was their response?
We did some responsible disclosure, and there's some communication back and forth, and again, it's like a tough problem because this is hardware that's already been deployed, and you can't swap out the image sensor for a different one that doesn't contain the inhibit standby for already deployed computers. So I will say the new Apple iSight cameras, new specs, new architecture, they're 720p, they're actually connected to the PCIe bus instead of USB, and so we have a new architecture, and they've had several different versions of the camera since what we studied, and so there is a hope out there, new architecture. And so that's future work that we're continuing to study.
Last question.
More of a comment, Jeremy Epstein, National Science Foundation. The old saying, those who cannot learn from history are doomed to repeat it. The same problem existed in the Sun 4 in the early 1990s. And those of us who were in the industry at the time recognized the problems of having LEDs that were software controllable, and they, as I recall, they did a pretty good job of solving it. So maybe it's time to study a little bit of history.
Right. Yeah, and in this case, like the sole purpose of the LED is for privacy enabling, and so we really need to focus and make sure it does that, and it doesn't fail us in this case. Thank you.
Thank you very much.